Hello, friends. Good evening, and welcome to my YouTube channel with my name Yugal Pachori. Um, and as you all know, that I'm doing PhD from IIT Mandi, and this is my current third year of PhD. And prior to this, I have teaching experience in Rajasthan Technical University, Kota, and AKTU. That is Dr. APJ Abdul Kalam Technical University, Lucknow. This is prior to doing my PhD from IIT Mandi. So at present, I have done almost 3 years in IIT Mandi, and today I am presenting you a very important topic that is known as either in some engineering college it is called basic electronics, but in system of IIT is called applied electronics. So I'm trying to give my views and thoughts. So it's a kind of a lecture on applied electronics, and whenever you get time to visit this video, you try to definitely watch this video. So let's start the discussion. I'm sharing my screen with you all. So you can see my screen in front of you. And the way we are going to discuss today is very simple. We will discuss the topic from a book that is known as Electronics Device and Circuit Theory. I have the PDF of this particular video, and I hope I am able to reproduce this video with the help of this particular video. So, this is the 11th edition of the book that is known as the Electronic Device and Circuit Theory. And you can easily download this book from the internet. And this book is from Robert L. Boylestad and Louis Nash Helskay. Nash Helskay. So it is a very famous book by the name of called EDC, Electronic Device and Circuit Theory. And famous, like first author Boylestad is a famous mean all those who are a student of electronics knows that this is the one of the famous book that is applicable in all the engineering college, whether it is IIT or it is non-IIT. It is in all the engineering college. So let's start our discussion today with this book. You can see this. These are the some significant equations. So I can skip this at this point of time. Let's come to the discussion, and you can see the name of the book is known as. So the like this is an introduction to. Initially, I'm discussing the introduction to applied electronics, applied electronics, EDC, EDC, EDC with Boylestad. With Boylestad, we are having our discussion with the book that is known as the Boylestad or the Electronic Circuit Theory. This is 11th edition of this book. You can see these are the two authors, Robert L. Boylestad and Louis Nash Helskay. So let's continue our discussion. And this is from the Pearson. However, you should have a copyright. You should not illegally reproduce. But if you have the PDF, then you can produce the content. Yeah. So this is the preface. Like preface is something like what talks about the book. Like this is the 11th edition. Then it will be what are the major things in this edition? What are the new changes? And what are the previous talks about the previous edition as well. So if you are a researcher doing PhD, then you must have a habit of reading the preface also, because BTech students generally do not read the preface. They directly come to the topic and they try to have a discussion straight away from the topic. But my advice to all the students is that if you're doing research or if you're doing masters, then you must read the preface of the book, because it talks about the structure of the book, how the book is written, and everything. So this is the preface of the book. I think we can move ahead for this preface. You can, like, if you want to have this book, you can easily download from the internet. It is available because our its reproduction is copyrighted. You cannot reproduce it, but you can read it and share the content with the person who wants the knowledge. So let's come to the topic. So these are the things. These are the some acknowledgement for the authors from the authors. This page is blank. Now come to the topics. What the topics this book covers of. This is very interesting. Friends, those who are a student of applied electronics or the basic electronics, they must read this book. This is very important book. And this is, let's discuss the topics today. The topic is semiconductor diode. I will, whenever in the coming sequence of this video or the coming videos, I will definitely go one by one. So initially, let's understand what are the topics. Topics are semiconductor diode, diode application, bipolar junction transistor. It is in short form, it is called BJT. DC biasing. Biasing means how you are connecting the BJT to the battery. There are various ways by which you can connect a BJT to the battery. So it is talking about the DC biasing. Then we have the BJT analysis, field effect transistor, or it is called FET. FET biasing, FET amplifier, BJT and GFET frequency response, operational amplifier, uh, operation amplifier or the 741 IC. This is one of the important topic. Then the applications of the operation amplifier, op-amp application, power amplifier. Generally, up to chapter 11, all the students need to study according to their syllabus. Up to chapter 10 or 11, it is very important. And beyond 12, 13, 14, 15, 16, some of the topics are related to the power electronics. So some of the colleges or some of the syllabus does not include beyond chapter 10 up to 17. But from chapter 1 to chapter 10, it is a must read book. And for other reference topic, you can also read this particular book for your benefit if you are a student of electronics researcher or and if you are a teacher, like for example, I have taught in AKTU and RTU, so I can, on the basis of that experience, I can say if you're teaching in some institute, then you must have a thorough understanding of this particular topic. Although I have also taken the lectures in IIT Mandi on the topic of applied electronics. So when I was taking lecture, I was very much prepared so the student get the idea what I'm trying to say or not. This is the thing. Now come to the just 1 second. I am just analyzing one thing that how much time I started this video. Okay, so this is already. Let me stop the share so that I will have the information. Okay, so it's working well. Now let's come to the topic of our discussion. I think it is 3:19, so almost I have a lot of time. So I can discuss the topic. So I have talked about the content of the book, and I've talked about the book as well. So it is a very good book, and if you are a student of yeah, so I have talked about the book. Now come to the topic. Now the come to the detailed description of the each topic. In semiconductor, you have the introduction means what do you mean by the semiconductor and what is a semiconductor? What are the application of semiconductor? What is a semiconductor diode? What are the materials by which what type of material is used in the formation of the semiconductor or the manufacturing of the semiconductor. Like for example, generally germanium, silicon, and gallium arsenide, and some other compound or mixture of semiconductor material is formed to form various types of semiconductor. So this is the thing, and yeah. So you can see this is the introduction, semiconductor material, germanium, silicon, gallium arsenide. Then you have the covalent bonding and intrinsic material. Then you have the discussion on energy level. So this one by one, this will come. So you can see this in the chapter one. So let's start our discussion. And this is chapter three, four. I have already told you that up to chapter 10, you have to thoroughly read this book. And beyond chapter 10, it is a choice according to syllabus, you have to read the book or not. So let's start our discussion with the our um, chapter number one. So let's straight away go to the chapter number one. What is the chapter number one is saying? So here's the semiconductor diode and became aware of general characters. What the this chapter number one will give to you? It will give you a lot of information related to you will be aware of the general characteristics of three important semiconductor material that is silicon, germanium, gallium arsenide. You will be able to understand what is silicon, what is germanium, what is gallium arsenide. Then you will able to understand the conduction using electrons and hole theory. Like you will able to understand what is hole and what is electron and how the electron uh, helps to constitute the current and how the hole helps to constitute the current. Because there are two types of charge carriers, one is electron and other is holes. Both types of charge carrier constitute the current in the semiconductor devices, whether it is transistor, diode, or any other device. Now you will have develop a clear understanding of the basic operation and characteristic of a diode in the no bias, forward bias, and reverse bias region. Then you will understand what is the mechanism or what is the working of the diodes in the three region. Basically, there are three region of let me annotate. Basically, there are three region. So you can see the three region. One is very simple. One is uh, forward bias. You can see this way. One is forward bias, then no bias, then we have the reverse bias. These are the things. So as soon as you come to know like what are the things and what not, then you can able to understand these things. So let me rub this annotation. Okay, now the annotation is rubbed. This is also rubbed. If you need any annotation, then I will use this particular uh, pointer for this particular thing. Okay, now come forward. Mouse. Now I have the mouse. Introduction. Introduction, I already told you. See, semiconductor, the discovery of the semiconductor, however, we things design text in 90 are still in use. A semiconductor is a very old device, and exact information that we can search over the internet or the uh, we can like I'm already sharing uh, the screen, so let me open the YouTube as well, Google as well, so you will be able to understand what is the when was semi. This is the question that I was talking about. Semiconductor was discovered in 1947 by John Bardeen and Walter Brattain and William Shockley at Bell's Labs. So you can have the understanding and you can make a note of all these things what I'm talking about. But the major source of discussion is this PDF of the book from the Boylestad, that is the electronic circuit device and theory. This is one of the important book, or you can say that like if I say religiously, then it is the Gita or the Bible or the Quran of the basic electronics. So this is very important. Now you now come to our topic. Uh, Come to the topic. You can see, yeah, I'm just adjusting. Edit, uh, hmm. Jacques Clear Kilby, inventor of the integrated. You can just look at this photograph. This is Jack St. Clear Kilby, inventor of the integrated circuit and the co-inventor of the electronic handheld calculator. So recently, just we saw in this particular like semiconductor was discovered in 1947 by John Bardeen, Walter Brattain, and William Shockley. But here we are talking about Jack Kilby is a co-inventor of the electronic Helen calculator from, and this image is taken by the Texas Instrument. So if you're giving this proper citation, then you can have the understanding of this particular topic clearly not. Why citation, friends? Because like suppose opinion is something different, but when you talk of technical things, then you must give the citation to the researcher and to the scientist and to the professor who actually discovered that particular concept or not. So let's come to our discussion on semiconductors. Semiconductor materials, there are three types of material: germanium, silicon, and gallium arsenide. And these are there are two types of semiconductor. One is intrinsic and other is extrinsic. Intrinsic mean it is in the pure form, and extrinsic mean it is the impure form. Uh, it will come into the book in the later stages, but I am continuing the discussion. That's why I'm telling you that there are two types of semiconductor. One is intrinsic and other is the extrinsic. Further, extrinsic are of two types, P type and N type. We will come to know what is P type and what is N type. On the basis of the doping, there are two types. One is P type and N type. Doping, I will tell you, but let's study the book. Semiconductor are a special class of element having a conductivity between that of a good conductor and that of an insulator. Now, this is a very important line. What is semiconductor? Semiconductor is a device which is having the properties or the conductivity between that of a good conductor and the insulator. Let me put the highlighter for you. Yeah, this is the highlighter. So semiconductor are a special class of element having conductivity between that of a good conductor and that of an insulator. This is the insulator. So let me change the color of the highlighter. It will be red. It is fine. Or reduce the size of the highlighter. Smart pen, finishing pen, line width. Yeah, this is fine. Width is fine. In general, I'm just trying this first time, so that's why I'm little bit taking of time. But you understood that what is semiconductor? What is semiconductor? And two types I already told you, extrinsic and intrinsic. Now the conductivity of the semiconductor lies between that of a conductor and the insulator. Conductor, those who are the student of electronics, they or the material science, they know what is conductor, and they also know the insulator. The conductivity of the insulator is almost zero, and whereas the conductivity of the uh, conductor is very high. It depends upon the free charge carriers. What kind of charge carriers there are available in the material? The number of the charge carriers are more in the conductor, and the number of the charge carriers are more in the less in the insulator, where the number of the charge carriers is moderate in the semiconductor. That's why its conductivity lies in between the insulator and the conductor. This is the discussion that I am talking about, and from the reference of this particular book, that is the Boylestad. Now, come to the next topic. The three semiconductors used frequently in the construction of electronics are silicon, germanium, and gallium arsenide. This I already told you. Let me rub this annotation. This is important because otherwise we cannot continue our discussion in the nice manner. We have to do this. And in this discussion, I'm trying to tell my knowledge, and what is the scope of your knowledge is depends on you and how the what are the sources that from which you are discussing. So let's continue the discussion. And it is not about that I am discussing. You have to blindly follow that. You can follow it, but you can trust your source of information as well. So I told you that semiconductors formed in 1947. Now this is the important structure of the covalent bonding and the intrinsic bonding. In semiconductor, covalent bond is formed. Covalent bond, you know, the bond between sharing and it required, and to complete the bond, you want eight electrons in the last shell. If you have the eight electron in the last shell, then it is a complete bond. Otherwise, this is incomplete. Suppose if you have four electron in the last shell, then you need at least four electron to complete the octet. And if you are not able to complete the octet, then it is not stable. And now, what is the point? Point is that if if you have two electron in the last cell, then you will be donating the two electron. And if you have six electron in the last cell, then you will accepting the two electron. So if you have more electron, then you accept, you become acceptor. If you have less electron, then you donate, because it depends on shell to cell, K to K element ratio or SPDF. This is taught in the basic chemistry in 11th, 12th, and even 10th as well. So continue the discussion. About the covalent bonding in semiconductor, we have the covalent bonding that is between the silicon, germanium, and the gallium arsenide. And you can easily understand from this particular structure, this is silicon, this is germanium, this is gallium, and this is arsenic. And just look at this one, two, three, four, five. Five valence electron. And gallium has one, two, three. So it will donate three, and this will accept three. But germanium, one, two, three, four. So it will share. So it will form the covalent bond. This, the bond of gallium and arsenic will be different, but the bond of silicon and germanium will be the covalent bonding. So majorly, we use silicon and the germanium. And out of silicon and germanium, silicon is more used because silicon is abundant in nature, and it has a one more thing that I will tell you, that it is abundant and is easily available. And there is one more reason I will tell you in the further discussion. Now come to this is the structure of the bond. You can see this is the bond structure. This is silicon. One electron, two electron, three electron, four electron. Now this is one electron, two electron, three electron, four electron. You can see one bond is formed, second bond is formed, third bond is formed, and fourth bond is formed. So it means the silicon is having the sharing of the electrons from its neighboring atoms. That's why it is written here it as covalent bonding of the silicon atom. Now, let's do the further discussion. In pure silicon of germanium crystal, the four valence electrons of one atom form a bonding arrangement with four adjoining atoms. Adjoining means nearby atoms. So it is clearly understood with this picture also, and the text is also written that it is formed the bond with the adjoining atom, as you can see in the figure 1.4. And this is from the reference of the book that is called the Boylestad. It is a very good book. That's why I'm making this video from PDF of this particular book only. And you can you can understand I can make PPT also from this particular book. But if you have the complete discussion from the book, then you can easily grasp the point from the PDF. That's why I'm directly sharing this video. But if I have something like I can make the PPT as well. There is no issue in that. But if you understand the discussion, then you will have the clear understanding of the concepts of the electronics that I'm talking about. Now, covalent bonding, this I've already told you in the discussion, and this is the bond of the gallium arsenide. Bond structure of the gallium. This is gallium, this is arsenide. You can see these are one, two, three, four, five. So, this is one sharing. This is one, two, three, four, five. So, structure of the covalent bonding in the gallium arsenide. Covalent bonding of the gallium arsenide crystal. Now, talk about the intrinsic carrier concentration. I in the beginning of this video, I told you that there are number of charge carriers in different semiconductor is different. So according to the types of the or the number of the charge carrier in gallium arsenide, you have 1.7 into 10 to the power 6 per cubic centimeter. Means per cubic centimeter you means per volume per centimeter cube per centimeter cube. So gallium arsenide you have 1.7 into 10 to the power 6. Silicon you have 1.5 into 10 to the power 10. Germanium you have 2.5 into 10 to the power 30. And if you talk about the mobility of the silicon is 1500, whereas the mobility of germanium is 3900, and the mobility of the gallium arsenide is 8500. So this is not the reason that why you prefer the silicon. However, the mobility of the silicon is less. But I will tell you that reason also that I'm just discussing that what is the point, why we prefer silicon. One reason is that it is mostly abundant. And other reason is that I will tell you as soon as let's Google it. So you will come to know why we prefer silicon over germanium. So silicon is preferred over germanium semiconductor due to its higher thermal stability and low reverse leakage current. Yeah. So these are the 2 points and greater abundance. Like you can, I am just highlighting these points. It is silicon is preferred over germanium in the semiconductor because due to higher thermal stability, it has more thermal stability and it has a less band gap and it has a less reverse leakage current and it is abundant in nature. This I already. So we have concluded our discussion. Now coming to the next point. The next one I told you the number of charge carriers and I told you about the mobility. You can easily understood. Now the come to the point is the energy level. So what I have discussed up till now is the introduction introduction to applied electronics. We have discussed semiconductor. We have discussed, now we are discussing the energy level. This is the short summary, what we have discussed up till now. Now, energy level. Friends, like I'm doing PhD in my third year of PhD. So my energy is considered to be the third year energy level. If I was in first year of my PhD, then my energy level is considered to be the first year of the PhD. If I was in BTech first year, then my first energy level is BTech first year. If I was in BTech third year, then my energy level is BTech third year. So likewise, electrons are also arranged in their energy level. So how they are arranged in their energy level, we will have the discussion. Hmm. So come to the next point, next page, semiconductor diode. Now you can see this from the diagram. This is the first energy level, second energy level, third energy level, fourth, fifth. Valence. So and how the conduction takes place? Conduction takes place only when you jump from the lower energy band to the higher energy band. For example, if you are here and you want to move from here to here, this point, from this point to this point, then only the conduction will happen. And you can easily see in this particular diagram that there is a lower band is known as the valence band and upper band is known as the conduction band. And the conduction is happening when this electron is jumping from valence band to the conduction band. And as you can see, this is the case of the semiconductor, sorry, insulator. But what happens in the insulator? You can see the energy gap. This energy gap is quite high, which is up to the order of the 5 electron volt. So the in the case of the insulator, uh, there are less chances that you able to cross the energy gap of the 5 electron volts. That's why the conduction rarely happen. That's why the conductivity of the insulator is almost zero. But whatever happens in the case of the conductor, there is overlapping. You can see the valence band is just touching the conduction band. And already there are some electrons which are present in the valence band and the conduction band both because there is overlapping. So that's why you just give a small amount of energy and the conduction happens automatically. But what is in the case of the semiconductor? You can see the energy gap is 0.67 germanium, 1.1 in silicon, and 1.43 in gallium arsenide. Uh, but why we prefer silicon? I already told you because it is more thermally stable. However, the energy gap is less in germanium, but the silicon is abundant. So there are the two reasons that why we are supporting for the silicon. That is, it is abundant and it has a higher thermal stability. So if you give some amount of energy to the electrons in the valence band, they directly jump or overcome the energy gap in the semiconductor and they reach to the point in the conduction band and hence the conduction happens. So that's why, according to the concept of the energy gap, there are three types of material. One is conductor, in which there is overlapping, and other is the semiconductor, where there is energy gap of 1 electron volt up to 1 electron volt, and in insulator there is an energy gap of 5 electron volts. So if you relate the three materials, that is conductor, semiconductor, insulator, it is the energy gap which decides the conductivity of the material. Hence, the conductivity happens in the conductor and the insulator. And because the energy gap is more in the insulator, that's why the conduction does not happen in the insulator. And to conclude the discussion today, we will continue the discussion in another. I will discuss the N type and P type in the another video. Uh, to conclude this, I will tell you what are the examples of the semiconductor. The example of the semiconductor you already know. I told you in the beginning of the discussion that is silicon, germanium, and the gallium arsenide. And what are the examples of the conductor? Every metal is a conductor. Like for example, silver, gold, iron, aluminum, copper. These are the examples of the conductor. Now, what are the examples of the insulator? Insulators are plastic, dry wood, not the wet wood, because if the wet wood has a water, then it will behave as a conductor. Dry wood is an example of the insulator, and the plastic and the bakelite are the examples of the insulator. Now, I'm stopping my discussion over here so that you can, and if you have any comment or suggestion, you can post in the comment, and if you can give your feedback as well. And I will come again, continue this lecture series in my next video. So thanks for watching and have a nice time.